Let's do a problem from your lab assignment. This is from section 11.11. This is problem number 1. We have a function e to the 2x squared, and we have a center point a is equal to 0. They have an n is equal to 3, and then we want to look at x values between 0 and 0.1. First thing they ask is to approximate the Taylor polynomial with degree 3, so this is going to be a cubic polynomial centered around 0. So Taylor polynomial formula is f of a plus f prime of a x minus a plus f double prime of a divided by 2 factorial x minus a squared, f triple prime evaluated at a divided by 3 factorial x minus a cubed. So we're going to need to find derivatives. Then we're going to need to evaluate those derivatives at 0. So this is your original function. The derivative of that is going to be itself times the derivative of the inside, so that's going to be 4x. And then the derivative of this will require a product rule. So I did this work a little bit on the side over here. We have the product rule. This is the first derivative. The second derivative is the product rule. So it's derivative of the first, which is just 4, and then e to the 2x squared, or e to the 2x squared, that's right, plus the first times the derivative of the second. And so the simplifying would be kind of useful to help us put in some values. So inside of the parentheses is 4 plus 16x squared. And then we go on to the third derivative. So this is our current function. Derivative of the first is going to be 32x times the second plus the first times the derivative of the second, and that's going to simplify to 48x plus 64x cubed times the exponential function. So when we do Taylor polynomials from scratch like this, we're going to be computing a lot of derivatives. And after we do the derivatives, we're going to have to put in our x, our a value, x equals 0 in this case. So in our original function, if we put 0 in here, we're going to get 1. So f of 0 is 1. In our first derivative function, we have an x in the parentheses, and so when you put 0 in there, that's just going to be 0. What is the second derivative? We put 0 in here inside of the parentheses, we're going to get 4 plus 0, and then whatever number that is, that's e to the 2x, e to the 0 is 1 again, so this is just going to be 4. And then the third derivative, we put 0 in for x, we're going to get 0, and so they've computed that for us, and we get 0. So therefore Taylor's polynomial, if we just plug in all these values, we have f of 0 for our first term, and then our second term, f prime of 0, it turns out the first derivative is 0. You don't need to put this. I'll temporarily put this and I'll take it out later. X minus 0. And then we have a plus, and then we have 4. That's the f double prime, and then we have to divide this by 2 factorial. And then we have an x minus 0 to the second power. And then we have the third one. This would be 0 over 3 factorial and all that, so this is going to be 0 again. We don't need all these zeros, so I'm going to take them out. And in fact, we have x minus 0 squared, so that's just x squared. And then 4 over 2 factorial is just 4 over 2, so it just really simplifies to this. So our third degree polynomial is actually a quadratic second degree. That's because the third term would have been 0. And our answer here is 1 plus 2x squared. So that's it for that first part. The second part, they're asking us to use Taylor's inequality to estimate the accuracy of the approximation where x lies in a given interval. So our given interval is between 0 and 0.1. So here's the remainder theorem that tells us, that helps us out, helps us figure out our approximation, how close our approximation is. Okay, so the first thing we want to do is we want to know if the fourth derivative is going to be bounded by some m. We want to know what that m is. We'll find that out in a minute, but we know that your remainder term is going to be less than that number, whatever that maximum is, divided by, well, it's really divided by the, this is R3, this is the remainder for 3, so we're really digging into the fourth term of Taylor's polynomial. So this is 3 plus 1, which is 4, and then that's a factorial, and then we have x minus 0 to that same power, 4. So this is our formula that we're going to use. And now we have the x value of that's between 0 and 0.01. And so we have the absolute value of x is less than or equal to, well, the largest value this can attain is 0.1. So let's put 0.1 there. And so if we take that to the fourth power, that's because that's what we're looking at here, to the fourth power. We're going to multiply this by 4, so this is going to be moved 4 places. That's 1, 2, 3, and then the fourth number would be 1. Okay, so now let's dig deeper into this remainder term. We want to know what the fourth derivative of this is. We've gotten up to 3 derivatives, and I've computed the fourth derivative here, which is going to be the same thing with an e to the 2x squared. And so the thing that's going to be inside the parentheses is going to be 48 plus 3, 84x squared plus 256x to the fourth. So that's your derivative. Now we want to find the maximum value of this within this interval. So there's a couple of hints that this is an increasing function. We have a 4th degree polynomial here, which is kind of like a, not a parabola, but like a u. And then we have an exponential function that makes it shoot up higher. So this is going to be the shape of a u-ish or parabola-ish kind of thing. And so this is going to be increasing from 0 to 0.1, which means the maximum is going to happen at 0.1. So f of 0.1 would be our maximum. By the way, it might be good to just take a moment to sketch a graph of this. I typed this in Desmos, and I can't see anything, but that's because when x is equal to 0, this is 48, so this is going to have to go all the way to 48. If you zoom out enough, you'll eventually see the beginnings of it, but of course this is not a very good view of it, and we're only concerned about the view from 0 to 0.1, so maybe we'll go a little bit farther than that, so 0 to maybe 0.5, and then I see a little bit of a graph that's a little bit more interesting here. So I'm interested in what happens at 0.1. Right here it goes up. That's 0.01. Let's go to 0.1. Right around here is probably going to be where I'm interested in finding that point. Okay, let's go back to our problem. and we have this thing here. So we can use this value. Therefore, the maximum value happens when you put 0.1 in for x. So m is going to be the value where you put 0.1 in for x in the fourth derivative. So it looks like we're going to need to figure out what this thing in parentheses. So they put 0.1 in here already, and they got e to the 0.02. So let's put 0.1 in here. I think we might need a calculator for this. So that's 256 times, and then we have 0.1 to the fourth power. So I think we want to go, well, this is already scientific. So it's 0.1 raised to the fourth power. And so we'll just say equals here, and then we'll add 384, and then 0.1 to the second power. So we have that, and then we add 48. So that's 51.865. Enter a number. Let's just enter the whole thing, 51.8656. And then we want to round this off. So we have this. Here goes our exponential. Let's start over again. So it's 0.02, and then up arrow, there it goes. So e to the 0.02 times the number that we got, 51.8656, and then we'll divide, or we can divide by 24 now, and then we'll multiply by 0.0001. So we have this number. Let's see. We want to round to 5 decimal places. This is in scientific notation. I think we can just move the decimal place 4 places to the left. 1, 2, 3, 4. So that's going to have 3 zeros. And then the next number is 2, and then 204. So I think that should be good. All right. So we have a really small error here, which is good. As we get larger Taylor polynomials degrees, then we have a smaller error. For part C, check your result by graphing the R of n. So remember the R of n? Oh, I think we graphed it already. So it's a parabola-like thing. Now we just have to make sure we match up. Oh, except the R of n goes down low. So it's not going down, so we can eliminate the first two. So it's one of these two over here. We want to see the graph at 0.1, and it's about 0.0002, and so I think this is a good candidate for this. The other one doesn't reach 0.0002 is right here, but it's not 0.01, or 0.1 is not farther away, so I think it's going to be this one in the corner. All right, so it's a little bit long-winded. There's a lot of steps to this. Whenever you're dealing with error, it's always really technical, and you have to be precise with your with your numeric calculations. Okay, I hope that helps.